Hello, my name is Carlyle, and this is my Lab 1 report video. In this lab, we tracked a ball moving at the same speed and in the same direction. On the screen, you can find more detailed information about my experiment. In this experiment, we want to see Newton's second law in real life. Newton's second law says the net force equals mass times the change in velocity, all divided by the change in time, with units of kilograms times meter per second. This law can be related to the momentum principle, which can be found on the screen. In this experiment, we want to display that there will be no acceleration for the ball if the net force is equal to 0, and the ball will move at the same distance per second for the entire duration of the trial. The goal of this experiment is to be able to predict the position of the ball at any given point in time, because the velocity will be constant and direction will not change. We will also be able to determine magnitude, which is how far the object moves per second in the direction of the motion, because we know velocity, position, and momentum, which are all vectors. Some observations I hope to make during this lab is constant and consistent velocity, direction, and magnitude. A few assumptions I made were that the net force would equal 0, meaning after the initial push, the ball would remain at a constant speed. Also, there would be no friction from the floor, air, and any other obstacles. Now I will discuss the connections with the fundamental principles. In this case, the system is the moving ball and the surroundings is everything else in the area. We will concentrate on forces felt by the systems from the surroundings. Like I previously mentioned, Newton's second law is F net equals mass times the change in velocity divided by the change in time, and the momentum principle is P equals m times v. There are a few other important equations also featured on the screen. These equations allow us to predict the positions and velocities at various times, which will be featured in the model. The graph shows distance versus time, which allows us to observe a consistent distance traveled per time. The model shows both predicted and observed values. The predicted values are orange and were determined from the GlowScript code, and the observed values are in blue, which is from the video and tracker. I chose this graph as my model because position versus time graphs have velocity as its slope, which allows us to easily determine if velocity is constant and consistent, and it also makes it significantly easier to predict values in the future. The GlowScript model also made a position versus time graph, which allows us to predict the future ball movements easily, which also corresponds very closely to the graph that I made. As I said, the graphs are very similar. They differ only slightly at the end because the predicted value was calculated using the initial velocity from the observed values. We calculated the initial velocity by subtracting the first position value from the second position value and divided them by the change in time. I then inputted this slope into GlowScript to calculate the predicted values because there was no acceleration to alter the velocity. If I were to improve this experiment in the future, I would make the roll longer so I could analyze more of the roll to eliminate possible accelerations in the future, or I would make the ball roll on a surface that has none or very little friction. Some possible errors in my experiment was the rough carpet, pushing the ball at an angle, or the ball continuing to accelerate after the beginning. This graph shows what it would look like if x and y were flipped. The graph would simply flip to the opposite direction. What does it mean? When F net equals 0, predicted values and observed values are very similar. It's difficult but not impossible to say how many forces are added together to get a 0 net force. In conclusion, Newton's second law and momentum principle are very similar and very crucial to determining the constant velocity of a ball in motion.